Hello everyone, now I'm going to present our research in a comparative study of deep learning models for financial news-based stock sentiment analysis. So, firstly, as there is many online news nowadays, as the internet grows, we as investors would read the news, easily access them, and get the information from the news, as well as an emotion from the news. Like when reading, we would like, oh, what's this? What's happening? And we will get worse or maybe happy that there's the news. So from that, we would execute a decision to buy or sell the stocks, which means that the news itself will impact the stock market. Prior study shows that Finbert combined with LSTM hybrids improve stock prediction accuracy. Then also, transformers such as the BERT family outperform traditional deep learning for financial sentiment classification. Lastly, embedding-based models such as Word2Vec combined with LSTM or FastText combined with LSTM shows competitive performance when properly engineered. And most research will get the news sentiment and classifies them to positive, neutral, and negative classes. A previous study on financial news sentiment analysis shows that sentiment analysis has evolved towards a transformer-based deep learning models, starting from lexicon-based approach, machine learning, and we start to go on deep learning. Then, secondly, it shows that transformers are effectively capturing semantic and contextual information. Lastly, financial sentiment is commonly modeled as a discrete classification, which is positive, neutral, negative, as stated before. Previous studies on sentiment-based stock movement prediction shows that when you combine sentiment analysis models such as Finbert combined with price prediction model, which is done by LSTM, it is improved the quality of the stock movement, where research shows that combining both Finbert and LSTM outperforms standalone SSTM and statistic models such as ARIMA. However, the sentiment quality prediction is evaluated indirectly via price prediction, making the contribution of the sentiment modeling difficult to isolate. Prior studies on sentiment-based stock movement prediction shows that transformer models outperforms traditional approaches in financial sentiment classification. Then also, embedding-based LSTM models remains competitive with proper feature engineering. However, existing work primarily focuses on classification-based sentiment prediction, with classes positive, neutral, or negative. There are three main goals for this research. First, we want to compare transformer-based models with word embedding combined with LSTM models for financial news sentiment analysis. Then, we want to predict continuous sentiment scores in the range of -1 to 1. And lastly, we want to justify regression-based sentiment modeling to capture sentiment intensity beyond discrete class labels like positive, neutral, or negative.
In this section, I will explain the methodology used in this research. The process includes data collection, pre-processing, model training for both LSTM and transformer-based models, and performance evaluation. Financial news articles were collected using the Markdown API with a primary focus on news from the United States. We used the news all endpoint to retrieve structured metadata such as news sources, related stock tickers, and sentiment scores ranging from -1 to +1, which were used as the ground truth labels. To improve efficiency and reproducibility, we implemented a local caching mechanism. This allowed repeated API requests with the same parameters to be loaded from this instead of querying the API again, reducing network overhead and dependency on external services. To obtain the full article text, HTML content was fetched directly from the publisher URL using a Cloudflare-compatible HTTP client. An automated article extraction framework was then used to isolate the main body text while removing the non-content elements such as advertisements and navigation menus. For articles that required account-based access, only the title and description were used as the textual input. In total, the dataset consists of 9,000 financial news articles with sentiment scores provided by Markto. For the LSTM-based models, text preprocessing was applied to standardize the input and reduce noise. This included converting all text to lowercase, removing punctuations and URLs, and processing emojis to preserve sentiment-related information. After pre-processing, the text was tokenized and transformed into numerical sequences using word2vec and fast text embeddings. Word2vec learns word representations based on surrounding context, while fast text uses character engrams, which helps handle rare words and financially domain-specific terminology. To ensure uniform input length, all sequences were padded or truncated to a maximum of 300 tokens, enabling efficient batch training and stable model performance. For transformer-based models such as Finbert and Albert, a different pre-processing strategy was used. Unlike the LSTM approach, punctuation removal and manual tokenization were not applied. The raw text was passed directly to the model tokenizer, which performs subword tokenization and generates input IDs and attention masks. This allows the transformer models to fully leverage bidirectional contextual information. After pre-processing, the dataset was divided into training, validation, and test sets. The training set was used for model learning, the validation set for hyperparameter tuning and early stopping, and the rest is used as a test set for final evaluation. The data was split using a fixed random seed with a ratio of 70% for training, 20% for validation, and 10% for testing, ensuring reproducibility and fair comparison across models. To optimize the performance of the word embedding-based LSTM model, we perform hyperparameter tuning using Optuna, which applies Bayesian optimization. The search space included optimizer type, learning rate, number of LSTM layers, hidden layer size, dropout rate, and the structure of fully connected layers. A total of 100 trials were conducted, with each trial trained up to 40 epochs. Early stopping with a patient of 3 epochs was applied to prevent overfitting and reduce unnecessary computation. Finbert, a pre-trained transformer model specialized for financial text, was fine-tuned for sentiment regression. The model was trained for 10 epochs using the Adam optimizer with a learning rate of 5 times 10 to the power of -5. This configuration allows efficient task adaptation while minimizing the risk of overfitting. Albert v2 was also fine-tuned using the same dataset to ensure a fair comparison with Finbert. Albert used parameter sharing and factorized embeddings, making it more parameter efficient while maintaining performance. The model was trained for 10 epochs with the same learning rate and optimizer as Finbert, allowing performance differences to be attributed mainly to architectural characteristics. Model performance was evaluated using multiple regression metrics, including mean absolute error, mean squared error, root mean squared error, and R-squared score. These metrics measure prediction accuracy, error magnitude, and the proportion of variance explained by the model. Together, they provide a comprehensive and reliable framework for comparing model performance across different architectures. This slide presents the regression performance of all evaluated models as summarized in this table. Among all approaches, Finbert achieved the best overall performance with the lowest mean squared error, mean absolute error, and root mean squared error, as well as the highest R-squared value. The Albert v2 model showed moderate improvement compared to the embedding-based LSTM model. In contrast, LSTM combined with fast text and word2vec produce higher error values and near zero or negative R-squared scores. Overall, these results indicate that transformer-based models outperform LSTM-based architectures for financial sentiment regression. Although Finbert achieved the best relative performance, the absolute error values remain relatively high. For example, a mean absolute error of approximately 0.21 means that the predicted sentiment scores deviate on average by more than 10% of the full sentiment range, which spans from -1 to +1. Additionally, the low R-squared values across all models suggest limited explanatory power. This indicates that a large portion of the variance in sentiment scores is not captured by the evaluated models. These findings highlight the inherent difficulty of performing continuous sentiment regression on financial news articles. One possible explanation for the low R-squared performance is the use of API-generated sentiment scores from the Mark II API as regression targets. Since these sentiment labels are generated by an automated model rather than human annotation, they may contain noise, systematic bias, and inconsistencies across articles. As a result, the maximum achievable regression performance is constrained by the reliability of the sentiment labels themselves. In this context, the evaluated models can be interpreted as learning to approximate the Mark II sentiment scoring mechanism rather than capturing the true underlying human sentiment. Another contributing factor is the relatively limited dataset size, which consists of 9,000 news articles. Transformer-based models typically benefit from much larger training corpora. Therefore, the limited amount of data may restrict the model's ability to generate complex sentiment patterns. This limitation is particularly relevant for fine-tuning large pre-trained transformer architectures. In summary, the results show that the transformer-based models, especially Finbert, are more effective than embedding-based LSTM models for financial sentiment analysis. However, the observed error magnitudes, consistently low R-squared score values, indicate that continuous sentiment prediction at the individual article level remains challenging. These findings suggest that models may be more suitable for discrete sentiment classification or aggregate-level sentiment analysis, which align with prior research in financial sentiment studies.
After conducting this research, we found 3 key points. Transformer-based models, particularly Finbert and Albert V2, outperforms embedding-based LSTM architectures for continuous financial sentiment prediction, where Finbert excels the most, since Finbert is trained on a financial corpus. Secondly, results demonstrates that Transformer's superior ability to capture semantic and contextual patterns in financial news. Then lastly, the proposed framework enables scalable sentiment extraction from large volumes of financial articles. After finishing this research, we concluded there are 3 main limitations in this research. Firstly, all models exhibit relatively low RT scores, indicating that article-level sentiment regression predictions remains challenging. Secondly, continuous sentiment labels in the range of -1 to 1 that is obtained from the Marketaux API may contain inherent noise and variability. Lastly, the models only partially capture the full complexity of sentiment expressed in financial news text. So, to address the limitations, we plan to do 3 things. Firstly, we want to incorporate name entity recognition for a better model for entity-specific sentiment prediction. Next, we want to explore a larger and more diverse dataset to improve generalization. Lastly, we want to integrate time series data with textual sentiment to better analyze the sentiment-price relationships. So, these are the references used for this presentation. As these presentations come to an end, thank you for your attention and thank you for listening.